Bien, ¿y usted?
¿Cuánto duró con esta responsabilidad?
¿Cómo?
¿Cuánto duró con
¿Cuánto duré yo?
¿Como un año?
Más. Luego, quedan por
Sí, me acuerdo.
bla, bla, bla.
Esto le ayudó mucho a...
A mí, cuando me puse un bárbaro, en un momento como con la secretaria, me dijo que como era más fácil que la gente te ubicara.
Sí, claro.
Que te ubique. Dos, entonces la interacción de gente que no necesariamente está aquí.
Uno saluda, pero ¿qué tal actúa? ¿Cómo estás? Con la gente, ¿no?
Muy bien.
Uno nunca interactúa con la gente, ¿no?
No, 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 no.
No, eso sí,
Entonces
eso
te
ya
obliga
pues.
un poco, ¿no? Y dos, estás obligado a venir a los seminarios.
Y sí, yo creo que sí habrá que darla en inglés, que sí vino Chani. Entonces, ella. Sí. Está bien.
Sí, pues sí, ¿por qué no?
Así, bienvenidos. No, ¿cómo se dice? Todos se sienten bienvenidos.
Bueno, buenos días a todos. Vamos a empezar con el coloquio semanal, el cual se lleva ya los miércoles a las 12. El día de hoy tenemos a Emilio Tejeda. Él terminó sus estudios doctorales en Trieste, en Italia, y en su primer postdoc lo hizo junto al grupo de Stefan Roswood en Estocolmo. En este momento está como postdoc trabajando con Sergio Mendoza. Emilio, si quieres, puedes dar la charla. Hay un consenso si la da en inglés o en español. Ustedes eligen.
Los que quieran español votan en inglés.
¿Sí?
English.
Okay.
Go ahead.
So, great. So, thank you very much for having me here and letting me speak a little bit about my recent work, which deals with tidal disruptions. So, this is work that I've been, for this project in particular, I've been working with this group of people during the last 2 years, more or less. And this is more or less the plan for my talk. So first of all, I will try to motivate the phenomena. So what is these tidal disruptions? What kind of things we can learn about them? Where can we find them, etc. Then I will talk about the numerical tool we are using to tackle this problem. So, and I will show that this is a complex problem, and essentially, it's difficult to simulate it from beginning to end with a single tool. So what we did was to choose this mixed approach that uses a Lagrangian code coupled together with an Eulerian code. And in that way, we managed to follow the tidal disruption event from beginning to end. And then I will talk about recent results concerning these tidal disruptions. And in particular, I will focus on the role played by relativistic effects on these tidal disruptions. So first of all, let us talk about the arena. So we are thinking about the nuclear cluster in galactic centers. So it's a very crowded environment. We have lots of things going on. In particular, there's lots of stars, all kinds of stars, compact objects as well. So we might find intermediate mass black holes, lots of neutron stars, lots of white dwarfs. And and of course, they are not static. They are just swarming like a swarm of bees. So they are going all around, and we can describe this system by, well, at the center of the cluster, of course, there is a supermassive black hole, no? And in our current understanding, we think that every single major galaxy contains a black hole in the middle, so sitting at its nucleus. And surrounding this black hole is this population of stars, and let us say that we choose a typical mass, a typical radius for these stars, and then we also have a velocity dispersion associated with this stellar population. So there are some interesting lengths or scale lengths that we can identify. So first of all, we introduce the sphere of influence of the black hole. So the sphere of influence, it's essentially where the stars realize that there is a huge black hole sitting in the middle. And it's defined where, or we can roughly define it, where the velocity dispersion is roughly equal to the escape velocity, from the black hole. So it's, well, it's this, that's the definition, and it's, well, as I said, essentially where the stars realize that there is a supermassive black hole. Then we can also introduce the collision radius, which is where the stars interact to one another. So because before they just feel, say, the combined effect of all the other stars plus the black hole and plus other things which are there, say, gas, etc. But they don't really, I mean, it's just an averaged potential. But say within this radius, then it's every once in a while the stars will come close to each other, so they will interact. Then, very important for the purposes of this talk, we introduce the tidal radius, and the tidal radius is essentially where the stars feel the tidal field of the black hole. And that means that you cannot treat them as point particles anymore, because now they will start to deform at this radius. So of course I will explain in more detail what I mean by tidal radius and tidal disruption, but this is like roughly where the, as I said, the tidal effect or the tidal field of the black hole affects the star. And finally, of course, we have the length scale of the black hole, which we can introduce it with the Schwarzschild radius. And well, in this diagram, they are not a scale, of course. If we introduce some typical values, say 10 to the 6 solar masses black hole, and then think about solar type stars with a typical value for the velocity dispersion, then we have these kind of values. And you can see that both the sphere of influence and the collision radius are huge compared to the other two radii. So say this is for this 10 to the 6 solar masses black hole, then we will have a sphere of influence of order half parsec, while the Schwarzschild radius is really, really small. So this is about, it's like four times the solar radius. So it's, I mean, even though the black hole is huge, its radius, I mean, its event horizon, it's not much larger than our sun. And then the tidal radius, we can see is just, say, 1 order of magnitude larger than the black hole horizon. And of course, again, the tidal radius depends very much on which kind of a star you're talking about. So if you have a very condensed or compact star, then it will be more difficult to tidally disrupt it, or even just deform it. So what are tidal forces? We are all familiar with the tidal influence that the moon exerts on us, on Earth, and that it's responsible of the tides, ocean tides. And essentially, it stems from the fact that the gravitational attraction exerted by the moon on Earth is different at different locations on its surface. So of course, the near side is attracted with a higher intensity than the far side. And at the end, what you have is this elongation, which is, of course, vastly exaggerated in this plot. But you have this elongation along the line of sight that joins the two center of masses. And then you have compressions on the other two directions. So And well, that will be very important for the dynamics of a tidal disruption. But well, as I said, this is exaggerated. In the case of the Earth, these tides are at the level of 1/10⁶. So it's really, really small effect. But what happens when the tidal forces that roughly go with the gradient of the gravitational attraction and then you multiply it by the surface of your object. So what happens when the tidal forces are roughly equal to the self-gravity of the star? So this is what, well, I mean, this is a way to introduce the tidal radius, and it's again the same definition I used above, and you can see it goes with a relatively mild power of the black hole mass, then it depends on the size of the star you want to disrupt, and it's inversely proportional to the mass of your star. So we're interested in this kind of regime where the tidal forces due to a central object are comparable to the self-gravity forces of your star at the surface, of course. So the standard picture for tidal disruptions was laid out in the 70s and in the 80s by many people, among them these people here. And essentially, the picture is you have a star that ventures too close to the black hole, and its pericenter distance is comparable or lies within the tidal radius. And when that happens, the end result is that you completely destroy the star, so it's tidally disrupted. So from being a compact object, well, I mean a spherical condensed object, self-gravitating object, it's just spread all over a huge volume. And roughly, I mean, in the standard picture, you will consider parabolic trajectories. That's because they are coming from very far away. So they are coming essentially from the collision radius. So it's when you have this swarm of stars, and say every once in a while, they will interact. And so they don't have really conserved quantity. So it's not like the solar system, that all the planets have always, more or less always, the same orbital parameters. Here, they will do some kind of random walk on the parameter space. So they will randomly change their, say, energy or their angular momentum. And when that happens, it can happen that one of these stars is then launched in what is called the Lowe's cone. So one of these stars plunges directly to the black hole, or very close to a radial orbit towards the black hole. So as I said, the star is totally shredded apart, and when you have a parabolic trajectory, then roughly speaking, for a parabolic trajectory is exactly half of the mass will be bound to the black hole, and half of the mass will be unbound. So say all these fluid parcels escape along hyperbolic trajectories, and then all the half of the star which is energetically bound to the black hole will eventually come back. And once you have disrupted it, then the individual fluid parcels essentially, yes, please. Yeah, so he asked whether it is really destroyed or there is something like survives. And that's actually a very good question. So in reality, of course, the star is much more condensed in the nucleus. So if the encounter is just mild, in the sense that if it is just grasping, say, the tidal radius, then you would expect that you unbound its outer layers, and then there is a surviving core. And those are called partial disruptions, and are also very interesting. I mean, it's a very interesting case. But here I will be more interested in the deep encounters. And in the deep encounters, you really disrupt the full star. And so in this case, once it is disrupted, then the individual mass parcels are essentially following ballistic trajectories. So that means that self-gravity is not important anymore. And when that happens, then it's very simple to, I mean, just by applying Kepler's law, you can infer or you can calculate the return rate. So the rate with which mass will come back to the black hole. And this is an important result. We will be seeing this expression often during this talk. So the mass return goes like t to the minus 5/3. And then this is crucial because one thing is the mass accretion rate, so the return rate, and the other is how you assemble or how you go from that flow which is coming back, it's debris flow which is coming back, how do you transform that into an accretion disk? And then, I mean, that's the standard picture, right? That the luminosity from this event will come from an accretion disk. But the question is how you form the accretion disk from the return rate. And the big question is, why should the luminosity from such a disk follow the mass return rate? So it's not immediately obvious that these two things should be comparable, because the accretion disk will evolve in its own time scale, which is set by the viscous time scale. So that's the big question, and then I will be using this parameter quite often. So it's the impact parameter, and it's related with your question. So it's essentially the ratio between the tidal radius and the presented distance. So when this parameter is very large, that means very deep encounter. When it is, say, 0.5 or less than 1, then it's a mild encounter, and then at most you expect some kind of partial disruption. Well, then I also mentioned that the tidal radius is a strong function of the kind of a star you have. So in this plot, I'm showing the tidal radius for different kinds of stars. So we have a red giant, a solar-like star, white dwarf, and a neutron star. So the y-axis is the presented distance, and on the x-axis is the mass of the black hole. And this plot is essentially, say, let us consider the blue line. So we are thinking of a star like the sun. So that means that if you lie above the blue line, then your presented distance is larger than the tidal radius, and you don't expect to see much disruption going on. On the other hand, if it lies below it, then the impact parameter is large, and you expect a violent event. So we can see, for instance, that since the Schwarzschild radius grows linearly with the mass of the black hole, and instead the tidal radius goes with the 1/3 power of the mass of the black hole, then eventually for a large enough black hole, the tidal radius will lie inside the event horizon, and that means that you don't disrupt the star. So the star actually will plunge all the way through the event horizon without noticing it, and then, well, it might be disrupted inside, but we don't care about that. So, and that's very important, because then it sets a maximum limit for the mass of your central object. So let us see, for a red giant, you can just read it. So that happens when, so 1 means event horizon, because I'm expressing the presented distance in units of gravitational radii. Well, it will be actually 2, no, for a non-rotating black hole. So we can see that the red line intersects around 9. So that means that you won't expect to see any disruption happening for a red giant, for a black hole with a mass larger than 10 to the 9 solar masses. Then for a star like our sun, this limit becomes around a little bit less than 10 to the 8 solar masses. For a white dwarf, it's pretty small limit. So we won't expect to see any kind of tidal disruption for white dwarfs in typical supermassive black holes, because you will. The impact parameter will be set by where you are with respect to the corresponding line. So say if we are with a main sequence star, and your presented distance is exactly on the blue line, then beta is equal 1. If it is below, beta is larger than 1, and if it is above, then it is less than 1. And then, well, neutron stars, there's no hope. You need a solar mass black hole to actually disrupt it. Well, yeah, please.
Suppose you could see the disruption Thank you. Suppose you can actually see the disruption of a neutron star. it would be quite an event. I suppose the neutrons would start to disintegrate.
Mhm. For a neutron star. Yeah, so it's actually something that might happen quite often, and people think it's related with short gamma ray bursts. So we are thinking about a binary system in which one is an evolved companion which has already collapsed to a black hole, and then you have a neutron star, and eventually they merge via gravitational wave emission, and you have this merger. So it's yeah, you're welcome. And then this shaded region means where we expect that relativistic effects will be important. So say below 100 gravitational radii, we expect relativistic effects to be order 1%. So important, but not that important. But below, if the presenter distance is below 10 gravitational radii, then the relativistic effects are already order 10%. So that means they are really important for whatever you want to study there. And this is a crucial point that I would like to stress. So notice that for a black hole like ours, which should be like slightly above the 6, any tidal disruption of a solar type star will be in the deep relativistic regime. So, and for any other black hole, which is at most 10 to the 7 solar masses, then if we see the tidal disruption of a main sequence star, then we can be sure that that took place in a relativistic regime. So as I mentioned, TDEs were essentially presented as some theoretical possibility, but nobody was really sure whether we will see them or not. And from the 1990s onwards, with these X-ray satellites, there were some X-ray flares that were started to be detected and couldn't be interpreted as standard or known things. And the crucial ingredient for their interpretation as TDEs was that they, the energetics are roughly what you would expect for a tidal disruption, but most importantly, the decay rate of your signal goes down with this power law, which is the same that it's the one that I said is very simple to obtain from Kepler's law. And so that was like the big hint to, for interpreting these things as TDEs. And well, after that, so these first discoveries were a bit a surprise. So they were not actively looking for these kind of things. But very recently, say from 2011 onwards, there have been different all-sky surveys looking for transient phenomena, which of course they are interested in all kind of transient phenomena like supernovae or other kind of flares, but they are also targeted at finding this kind of tidal disruption events. So nowadays, there's something like 30, a little bit more than 30 candidates for TDEs. They have been found mostly in the soft X-ray with soft X-rays, but they have also been identified with ultraviolet, optical, and there's even 2 cases which have been observed with Swift satellite in the gamma ray band. And those 2 cases are actually interpreted as launching relativistic jets. So, well, yeah. So that's a very good question, of course. So in principle, we expect these tidal disruption events going on every kind of galaxy. But if you have an active galaxy, of course, it will be very difficult to tell apart a signal like this from the overall AGN activity. So these probes are actually biased towards inactive galaxies. And that's good news because, I mean, I started saying that our current understanding is that every single galaxy contains a supermassive black hole. But there's actually not hard evidence for this fact for, say, galaxies which are not, or which are, say, 10 to the 5 solar masses black hole, solar mass, yeah. And so this is like an excellent probe for studying inactive or quiescent black holes. Well, so this is just a summary. They typically, when they are detected in X-rays, they are typically detected in the soft X-ray band, so with these kind of energies. They have luminosities, which are between 10 to the 42 and 10 to the 45 ergs per second, and that places them slightly, well, I mean, above supernovae and slightly below AGN activity. They fade out in times which are other months, years, and they follow this law. They have been observed in relatively nearby galaxies, so these are the kind of redshifts. And as I said, there is, in a couple of cases, there is evidence of relativistic jets being launched, and that implies, or that necessary, well, that implies that there's some kind of super Eddington accretion going on. So the TDEs are a fantastic tool for studying, as I said, supermassive black holes in quiescent, quiescent black holes in inactive galaxies. They are also, of course, a good probe for intermediate mass black holes. So so far I've been talking about nuclear clusters, but the same could happen in a globular cluster, right? And some people believe that in the center of some globular clusters, there might be an intermediate mass black hole sitting there. So the same should happen as well there. Then there's some detection of a TDE-like curve, which had some peculiarities, and it was interpreted as a TDE coming from a binary system. So you have a supermassive black hole binary system. Well, and also, as I said, they take place in the relativistic regime, so that means they are an excellent probe for the strong gravity regime. And if we model them, I mean, if we are able to model them appropriately, say if we understand the physics going on with the TDE, then we are in a position to learn about the black holes. So we can infer some black hole parameters like its mass and its spin. And most importantly, we can also test GR theories and see whether the thing which is in the middle of the galaxy is actually a black hole or not something more exotic, like a cluster of very compact stars or a cluster of intermediate mass black holes. Well, but TDEs I mean, our current understanding of TDEs is just starting, and it's being like excited. Well, I mean, triggered thanks to observations. So we have some observations, and many hundreds or thousands of new observations are expected to come in the near future. So there are still many challenges. So, and I will focus on these four. So first of all, how is it that the luminosity that we observe follows the mass return rate? Then there is also a mismatch between the total emitted luminosity. From theoretical predictions, you expect something in the order of 10 to the 53 erg, and instead the TDEs observed so far have more like 10 to the 51 erg. Then there's also a mismatch with the event rate. So from different theoretical calculations, you expect something like 1,000, one event per 1,000 galaxies. So that means 10 to the 4 per galaxy per year. And instead, I mean, of course, the numbers are too small to do any kind of study, but well, so far we are seeing something like 10 to the 5 events per year per galaxy. Yep.
Like
Mhm. Yeah. Yeah. So for sure, in events like the ones we were talking about before, so black holes with neutron stars, then you expect that lots of the luminosity goes away in the form of neutrinos. But for main sequence stars, the kind of, I mean, once you, well, I mean, we don't know, but say once you have formed an accretion disk, the kind of temperatures and densities that you form are well below the ones needed for emitting neutrinos. So I mean, they are emitting just in the soft X-ray band. So it's probably they don't play an important role for, say, main sequence stars being disrupted. Well, and there are also many ingredients that we need to take into account. So general relativity, self-gravity of the gas, which of course is very important before you disrupt the star. Once you have disrupted it, the star, which was a condensed object now, has a complex geometry, and it spans several orders of magnitude in time scales and densities. Of course, if you want to build an accretion disk, our standard understanding of accretion disks is that you need some kind of magnetic field to operate and drive the accretion within it. And eventually, if you want to connect this with observations, of course, you need some kind of radiation transport in your code. So this is just well, I mean, this is a figure from an actual simulation of a tidal disruption, but just take it as a cartoon. I don't remember the values right now, but it was probably a main sequence star being disrupted. So initially, you don't even see it at this scale because it's so small. So it has come. The white circle is the tidal radius of the black hole. This was a partial disruption. So that means that you remove some part of the outer envelope, but at the end, there is a surviving core. And so this is a pretty challenging situation because, of course, the mass in the remaining core has a very small time scale. It's evolving in a small time scale, while these tails are evolving essentially in free expansion. They are not feeling the self-gravity anymore. Well, okay, so the conclusion is that numerical simulations are essential for studying these systems. So there are different options, and people have tried different options. So one is to stay in the Newtonian regime, so study TDEs happening in a Newtonian regime, or introduce some kind of pseudo-Newtonian potentials to mimic some general relativistic effects, use post-Newtonian approximation, go to the full GR regime, which is, of course, who knows if it is a wise decision, because once you have disrupted the star, of course, the dominant source of gravity will be the central black hole, and the star is negligible. But on top of that, you are evolving the Einstein equation, so it's really, really time-consuming to do that. And do some combination of the previous options. And that's actually the work I will talk about. And as we used first, well, I will go to that later. So this is just a brief cartoon to stress the role played by relativistic effects. So what you are seeing here is not a star, it's just a ring of test particles. So I start with a small ring of test particles and let it fall towards a black hole along towards a central object along a parabolic trajectory. And then if you see the Newtonian trajectory, yeah, I mean, this is like a graphical representation of the tidal radius, tidal tensor. Yes, please.
This cloud is not self-gravity?
No, it's just a ring of test particles. And you can see how it's deformed as it approaches the black hole, and then it oscillates, or, well, I mean, it has some peculiar shape, but it's essentially circular after the encounter. Instead, the very same, I mean, the exactly same ring, if you follow it in a Schwarzschild, the geodesic trajectories around a Schwarzschild black hole, then this is the shape that it does, that you form. And it's dramatically different from the Newtonian result. You can see all this expansion and deformation and like this crescent form that it's receding away from the black hole, it's totally due to relativistic precession of pericenter. And well, the red curve was just the center of mass. So what will be the center of mass of this ring? No? And you can see that it's roughly always, well, I mean, here, of course, there's much more mass than on this other branch. Okay, so first of all, I will talk about, as I said, we decided to tackle this problem with a hybrid approach, and we will follow the tidal disruption itself with an SPH code, which is a Lagrangian code that follow, I mean, it samples the fluid as particles. So they are called SPH particles, and they sample your fluid. And we have, so we took a Newtonian SPH code, we modified it in such a way that now the gravity, sorry, the hydrodynamics is fully relativistic, but we are still dealing with self-gravity in a la Newton. So we have these, I mean, of course, it's an approximation, right? So this part is fully relativistic, but once you add a Newtonian description of self-gravity, it becomes just an approximative approach. And well, it should appear soon, and it's developed for both rotating and non-rotating black holes, and you can use different kind of coordinates. So we benchmarked this new code against known relativistic solutions or simulations. So this is a paper by Kobayashi, Laguna, et al. From 10 years ago. And this is, well, of course, we try to do it, I mean, orient everything on exactly the same parameters to stress that we are exactly reproducing the same results that these people got 10 years ago. So here is 3 encounters with different betas. So beta 1, beta 5, and beta 10. You can see that beta 10 is really, really extreme and goes around the black hole like once due to the pericenter. Yes. So the higher the beta, the deeper the impact. And you can see, so this circle is tidal radius 1. So beta 1 is just grazing the tidal radius. Then we followed the tidal disruption of a star around a rotating black hole. In this case, is in the equatorial plane. The arrow points along the spin of the black hole. And you can see that qualitatively, there's not much news with respect to the Schwarzschild case. But this changes once you allow for a misalignment between the orbital plane and the spin of the black hole. So this was pi halves, so perpendicular. Now we have a little bit of inclination. And one thing that happens around a rotating black hole is that you don't have an orbital plane anymore. So now you're, if you think of individual particles, their plane will, it is said that their plane precesses. So now they are not contained along a plane. And well, this is one case, and a much more dramatic case. You will see that now the crescent is totally different from before. I mean, qualitatively different from what we were seeing before. So you have this kind of S shape. And then we were happy exploring with this. I mean, this might not be the most realistic scenarios, but then we wanted to try the disruption of a white dwarf by a 10 to the 6 solar masses black hole. And well, and this was a really, really deep encounter. So the pericenter distance was only 1.5 gravitational radii. So that means that it went really, really close to the event horizon. And well, the end result is this crazy shape. And yeah, of course, we are modeling all this with polytropes. So, and if you want to do any realistic analysis of this, then you need a more complicated, well, I mean, a more realistic equation of a state to see what's really going on with the white dwarf after it is disrupted in such a way. Yep. Yeah. No, not directly. So we can post-process them. So they will play minor role for the dynamics, but of course they are an important signature, and it is expected. If they were a binary that is evolving for a long time, then they are crucial. But here is just serendip. What is the word? I mean, it was just by chance that the star approached the black hole. So at that time, there's not enough time to release energy in gravitational waves, but I mean, a substantial fraction of the energy. But there will be some gravitational wave emission. And so we can post-process our simulations and see what will be the spectrum of the resulting gravitational waves. Then, as I said, our approach is an approximation, because we are putting Newtonian self-gravity on top of a relativistic hydrodynamics code. And that means, well, it's just an approximation. And one of the first things that you lose is covariance. That means that now the simulation will, I mean, in principle, the output or the outcome of the simulation might depend on which coordinates you decide to use. So maybe, well, I mean, it's just a proof of principle. So how much we are violating covariance with this approach. So what we did was to follow the same disruption with these parameters. So a solar mass star around a 10 to the 8 solar masses black hole, and we follow it with two coordinates, Boyer-Lindquist and Kerr-Schild. And then you can see here, this will be the parabolic Newtonian trajectory, and instead these are the relativistic trajectories, and you can see that they are different, but not that different. So we can live with this, because this is a really deep encounter. So yeah, there's some difference between the two curves, and then if you study the end result, the mass distribution of the star, again, they are, I mean, qualitatively, they look the same in these two coordinates. And very importantly, we got that in the relativistic simulations, 100% of the mass was disrupted. So this percentage here represents the amount of mass that is still bound. And in the Newtonian simulation, we had essentially a full surviving star, so it's 99%. And then in the relativistic regime, you have full disruption. Am I running out of time? Okay. I will rush a little bit because I want to go to the new results. So I will skip this. So this is what we did. This is, you can see this article if you're interested in more details. So as I said, we followed the initial phase, the disruption phase, with a Newtonian code, with the SPH code. And then, once self-gravity stops to be important and play an important role, we mapped the final distribution into a grid code, which is this coral code, which is full relativistic, can follow radiative transfer, and has magnetic fields incorporated. So this is our parameters. We studied, we chose these values because they were convenient for our simulation. So it's a red dwarf, around a 10 to the 5 solar masses black hole. This is a very deep encounter, as you can see, beta equal 10, and it's not parabolic. It's slightly elliptical trajectory. Well, not so slightly. It's elliptical trajectory. And so here is just a rough, summary of the SPH simulation. So the green line would be the Newtonian ellipse, but now we have pericenter precession, and you can see, well, this is how the disrupted star looks like at the end of the simulation, of the SPH simulation, and we took this snapshot and mapped it into the coral grid. So this is the last snapshot. We mapped it into the coral grid. As I said, once we have disrupted it, now each individual fluid parcel is following a ballistic trajectory. So it has a well-defined pericenter distance, apocenter distance, eccentricity. And so you can see that after disruption, all these quantities are roughly symmetrically distributed around the initial values. So this is the pericenter distance, the apocenter distances. So they are order 500 gravitational radii, and then the eccentricities. This is a movie of the second part of the simulation. And there are many interesting things that I would like to discuss, but maybe we can talk about them later or in the questions. So essentially here you are seeing the XY plane, and then here is a cross section, XZ plane, and then here is the accretion rate. So how goes the accretion rate onto the black hole? So you can see that initially there was like a spike, and then it goes roughly low. Also, initially there was a very strong interaction. So it is, you can see that the head of the stream is working heavily on the rest of the debris. And if you are careful enough, you will see that there is some kind of periodicity going on there, and that will be important.
These are hours?
Yeah, there is hours. So the full simulation is something like 16 hours. And then it changes completely. So, it was an elliptic encounter. So all the mass came back in a finite time, and you formed an accretion disk. So now you have, it's turbulent, but the geometry changed dramatically from the first phase to the second phase. So roughly speaking, we can divide the simulation in two phases, which is this one. And so you have this, the formation of a dissipative shock, which is ejecting lots of matter. And so this is a collision going on at 0.2 and a relative speed of 0.2 the speed of light. So it's really strong collision. And from that, you dissipate lots of energy. You actually emit some kind of wind, radial, quasi-spherical radial wind. And you also, some gas elements gained a lot of energy. Others lost energy and were directly accreted. And there is evidence of this periodic feedback loop that I don't have time to explain, but it's nice. And then the second part, I put circularization because that was our expectation. So we were expecting to see how the debris circularizes into disk. But actually, it's not circular at all. So there is some, it's a torus. There's, of course, some axisymmetry. But if you follow the trajectories of fluid particles inside the disk, they are moving like crazy. So they are not moving in circular orbits. So that was against our expectation, our initial expectation.
What is the plane of the direction? Is this way or that way?
Here there is no rotation, black hole rotation.
No, but the plane of the orbit.
XY, in these coordinates. So here is a close up on the self-crossing, and so this is density, and here you can see in entropy that you are really, it's a really dissipative shock. So you are producing lots of entropy at the interface of these two fluids, and then, as I said, you are blowing out a radial wind. And, well, let me just, so you have the torus, the final torus is very hot and is supported by pressure. So you can see here is the angular momentum profile of our torus, and it's well below the Keplerian value. So that means that centrifugal forces are not sustaining the gas. So it's really the high temperature. And then,
what is the temperature of the torus?
where it comes from? It's 10 to the 7 Kelvin, but you shouldn't trust that much. Yeah, but in any case, yeah, and yeah, there are some caveats related to that, but yeah. And then this is a standard disk, and so in a standard disk, I just drop 4 particles and see what they do. No, I follow their trajectories. So you can see that they are roughly circular, but they are slowly spiraling into the black hole. No, it's a standard accretion disk. Instead, in our torus, I dropped 4 tracers exactly at the same location as before, and now you can see that they are following very peculiar trajectories. And actually, this torus is not accreting at all. So it has a very low accretion rate, even though that's another surprise. Well, sorry for going so fast at the end, but I will be happy to answer questions. But this is how the eccentricity evolved during the simulation. And as I said, our expectation was that all the fluid will circularize eventually, right? So that means that all the eccentricities will go to 0. And instead, after several timescales, and the disk was not really evolving anymore, we had this final distribution of eccentricities. So you do have some circular orbits, but you still have particles or fluid parcels that have really large eccentricities. A big surprise was that magnetic fields played a secondary role, or a really negligible role. So we expected to see that the hydro simulation will not have any accretion because we didn't have any mechanism to drive it, whereas the the MHD simulation will have, eventually will say, start to form the MRI instability, and that will drive accretion towards the black hole. And our big surprise is that, I mean, this is a simulation, the hydro simulation, this is a MHD simulation, and essentially, I mean, roughly the numbers were the same. The accretion rates, the turbulence level, just so you can see here the accretion rates for both simulations.
How did you choose the strength of the magnetic field?
Yeah, so we, of course, the first part didn't have magnetic fields because our SPH code is not able to do that. So when we did the mapping, what we did was to see a very low-level magnetic field, which is like loops, poloidal loops, which are concentrated where the density is highest, but the magnetic pressure was set at 1% of the hydro pressure. So I mean, this is completely put by hand, but our expectation is that it is so low that it will eventually grow as the disk tells it to grow. So that's our answer with the magnetic field. Yes, and so this is the accretion rate towards the black hole. Then this is the mass that survives in the torus, so these solid lines. And all the rest, about 40% of the mass, is lost in this radial wind I was talking about. Okay. Okay, so just my conclusions. Yeah. As I said, there were some issues. Well, I mean, there are several issues with TDEs, and I didn't argue so much about why, but our simulation, it was a very extreme relativistic encounter, but it might possibly point to the solution to some of the problems with TDEs that I mentioned initially. So for instance, why the luminosity follows the return rate. So if you expect the luminosity to come from a disk, then it's not so obvious why it should follow it. But then, if the luminosity comes from this strong shock that is formed at the interface of the two debris, then that shock obviously follows the return rate. So that's one possible explanation why the luminosity follows the return rate. Then why it is low level is because it is low level if you expect it to come from a standard disk. But we're seeing that the disk is not really accreting, is not really evolving. So if all the luminosity came only from this interaction phase, self-crossing phase, then that means that it will be a fraction of the energy budget that you were expecting. And finally, of course, some tidal disruptions will happen in a relativistic regime, others will not. But what we are seeing is that this strong interaction only happens in the really deep relativistic regime. And that means that then a fraction of the total TDEs that you expect will not be visible in this way. So only those that took place in the relativistic regime will lead to what we observe as a X-ray flare. I mean, this is very speculative. So it's just extrapolating from this single simulation, but it's a way.
Okay, let us thank to Emilio for a nice presentation. Slides in Spanish and speech in English. Questions, comments? Okay. In Spanish or English, there is no problem.
You mentioned there was a kind of an oscillation in. Could you explain this, please?
Yes, thank you. So let me put the movie. because it's easier to explain it with the movie. So please note that the head of the stream is like bouncing against the rest of the stream. So what we are seeing is that you have, you have fluid elements that had a really small pericenter distance. That means that they had a lot of pericenter shift. So they are colliding with the rest of the stream at a low angle. So they are injecting a lot of angular momentum. So the result is that that stream that was perturbed will be moved outward. That means that it will have a larger pericenter distance, less pericenter shift, and so it will collide further out. So this collision will be less efficient or less strong. But then again, some fluid parcels were not so strongly affected as before, so they will have small pericenter distances, and so this is a loop that is repeated. And it's actually visible in this curve. So this is a mass flow that is leaving a sphere at 100 gravitational radii. And you can see that it's imprinted, this periodicity is imprinted in this outflow. And the periodicity is, corresponds to the Keplerian orbit of a circular trajectory in this interaction radii, so around 30 gravitational radius.
Question. Did you mention if the simulations were 2D or fully 3D, because maybe the evolution of the magnetic field effect will be very different?
Yeah, of course, no. The two phases were full 3D simulations.
Emilio, just to make sure that 40% of the mass is lost. In fact, it doesn't go. That doesn't go to the black hole. Yeah.
Mm-hmm.
This number is can change according. It's a number. What's the certain?
No. Of course, TDEs depend strongly on the orbital parameters. So that's. All the numbers change dramatically if you change the kind of orbit. But the big surprise was that here we had, we were not expecting to see any substantial outflow because the trajectory was initially elliptic. That means that all of it was bound. So we were expecting to see like a really thick torus. And so it was, and this outflow was, it came about from this strong dissipation at the collision radius.
Yeah. And this outflowing material, I guess it has a lot of momentum, angular momentum. Mm-hmm. It's expanding, yeah? So, and it could drive gravitationally to other stars that are close, or even dark matter. If there is a cusp of dark matter around the black hole, this could be a mechanism to expand.
I don't know about that.
It's interesting, but
also taking into account that it's really, in terms of mass, it was a 0.1 solar masses black hole. So if 40% of it was lost, it's really, I don't know about galactic centers, but I think it's not so much mass to
feed the.
Yeah. But of course, it was only 1 TD. Maybe you have more.
Emilio, when you simulate this kind of tidal disruption events, are you taking account some kind of observed objects, or are based only on theoretical issues? Can you compare your results with the observations?
Yeah. So as I said, there are some observations, but it was not our aim in this project to tackle any particular TDE that has been observed. So we essentially chose, the simulation itself is a complex task. So we chose parameters which were easy to simulate. So that's why we chose a bound orbit, because that means that everything is within a single box.
It's interesting with the accretion rate changes, that you expect some kind of increase of the brightness in a particular band. For example, you mentioned the optical band or the Swift bands, X-rays band. How can you compare your results with that?
No. The parameters that we chose were probably unrealistic. So But I mean, we are trying to make the point in the article that you can learn some things about this and you can extrapolate to more realistic encounters. So for instance, this periodicity most likely will not be preserved in a more realistic encounter, unless it is really relativistic. So I mean, you should take all of this with a grain of salt. So it was only one simulation and probably an unrealistic one.
Do you see any evidence for a magnetically dominated outflow beginning to start, like a jet-type ejection?
No, not at all. And that was a huge surprise for us. So, as I said, the magnetic field played a not even secondary role. And well, it could be how we feed it, not how we seed it. So it was, I mean, we wanted to put it very low level because we had no idea about its structure. So it might be that if you disrupt for some reason, highly magnetized star, then you will see something different. Or if there is, some people believe that maybe there is a relic disk which has some magnetic field in it. So once you disrupt the star, you feed that disk and you in a way resuscitate it. And you use the magnetic field which was there.
Okay, 1 second.
About the magnetic field, I mean, I'm surprised. Do you have previous results for the same code when you do see the magnetic field growing?
Say again.
I mean, I'm worrying that you're handling the magnetic field correctly. So do you have previous papers on the same code where there is a magnetic field effect?
No, I mean, this is the first, I should mention that. This was actually the first TD simulation that took into account magnetic fields. So at this point, there is no standard.
No, but the same code. Maybe the same code did something
sure.
completely different with magnetic field,
sure,
and the
course.
magnetic field had a huge effect.
This code, this coral code, is used for standard disks. And there they develop the full
And
MRI.
they get the MRI, okay.
They see how it grows, and yeah. So here you can see this is an analysis of the disk. And so we just try to estimate an effective alpha parameter for the evolution of the disk. So here is the total alpha that we see. You probably cannot see it, but it's really low. So it's at the level of 0.1. And that's the total. While, and at the same time, the magnetic field is 2, 3 orders, no, just 1 order of magnitude below that. So it's not really growing with time. Or it's, well, this is, time is, green is early time, red is late time, and then this is the radius. So how this effective alpha parameter changes with radius. And you can see that it grew from the green to the red, but it's still 1 order of magnitude below the alpha coming from the purely turbulent environment of your torus. So it's growing, but not quickly enough.
Mm-hmm.
Hi, congratulations for your results. And I want to know what is your future work? I mean, what is the thing to want to improve it?
Yeah, so I'm very much interested in studying what's the role of the spin of the black hole. And we can do that now because both our codes, so the SPH part and the coral part, both are perfectly okay with the spinning black holes. So we just need time and someone, well, I mean, we need a machine. Well, there was some problems, but that's our next project. So running the spinning case.
More questions? If there are no more questions, let us thank again to Emilio.
Thank you.